We will start talking about Chapter 12 by introducing acids and bases and how we define acids and bases, at least for this course, using water as an example of both an acid and a base, move on to strong acids, strong bases, pH and the pOH scales, and then weak acids, weak bases, and finally talk about buffers, just slightly. For our definition of acids and bases, we are going to talk about the Bronsted-Lowry model. The Bronsted acids and bases are defined in terms of whether they donate or accept a proton, and a proton meaning an H plus ion. Right? So a proton is a hydrogen atom without its electron, so it's an H plus ion. A Bronsted acid is a molecule that donates, so gives off a proton, an H plus. A Bronsted base is a substance that accepts a proton, so takes in an H plus. Let's take a look at this reaction here. So we have ammonia and HCl, and it produces NH4 plus Cl minus. Well, if we look at this, how do we get from NH3 to NH4 plus? Well, I'm increasing the hydrogen count and I'm getting a plus sign, which means that NH3 plus H plus gives me NH4 plus. Therefore, NH3 is accepting a proton. Because it accepts a proton, it is a Bronsted base, and the acid, therefore, is going to be HCl, because HCl is giving off an H plus, and what's left over is a Cl minus. So its proton is H plus is given to the NH3, which accepts it, and it's a base, and HCl is my acid. Note that HCl is a neutral compound, but if it loses a proton, an H plus, it loses the hydrogen, but it also loses a positive sign. So if it's a 0, minus 1, right, that's a 1 from the charge of the hydrogen. What's left over is the chloride anion, Cl minus 1. When a Bronsted acid donates a proton to a base, right, to another substance, what is left over from the acid, so my original acid gives off a proton, what is left over after the donation, that is called a conjugate base. So let's look at an example. Here I have HCl plus a water giving me H3O plus Cl minus. Okay, well, what is my acid and what is my base? HCl is giving off this proton, this H plus, to the water, leaving me with a Cl minus. Since the HCl donates that proton, this is my Bronsted acid. This is my original acid. Now, what is it left? What's left over after this acid donates the proton? Well, I have Cl minus. That's what's left over from the original acid. This Cl minus, what's left over, is called the conjugate base of my original acid that I started with. So we will have a pair of Bronsted acid and conjugate base. Here's kind of what it looks like as a schematic. This is my acid because it loses that proton and it gives it to the water. And what's left over is the conjugate base of that acid, so Cl minus. Water acts as a base, as a Bronsted base, because it accepts that proton from HCl. Now, what is formed after the gaining of the proton, which is H3O plus, This is the conjugate acid of my base. So we have two pairs. We have the original acid and its conjugate base, and the original base and a conjugate acid. These are not to be confused, right? Acid with a conjugate acid and base with a conjugate base. These are not the pairs. The pairs is the acid with what's left over when it donates, the conjugate base, and the base with what is formed when it gains that H plus, the proton, forming the conjugate acid. When a Bronsted base accepts the proton from another substance, it becomes a conjugate acid, and we mentioned that. But here's an example. So if I have ammonia in water, I get NH4 plus OH minus. Well, what is happening here? Ammonia is accepting a proton from the water, giving NH4 plus. And water is giving off a proton, forming OH minus. That's what's left over when water loses a proton. So NH3 gains a proton, so it must be acting as a base, acts as a gains a proton, and gives me the conjugate acid. That's what is formed after the gaining of the proton, the conjugate acid. The original water that acts as an acid, the Bronsted acid, and what is left over after it loses a proton is OH minus. That is the conjugate base of the acid. So we will have two pairs. Note how to easily kind of tell whether, for the base here, what's the conjugate acid? Well, it looks very much like the base. It's got an H plus extra. For the acid, well, it still has the OH, right? It's lost one of the hydrogens and a plus sign, right? But this is still part of the water. This isn't part of the NH3. It doesn't look like the NH3 molecule or part of the NH3 molecule. So that's kind of how you can tell whether they belong together or not. And then when you determine which one is gaining the proton and which one is losing, then whatever's left over from the losing the proton is the conjugate base of the acid. Whatever is formed when the proton is gained, that's the conjugate acid of your base. Let's try a sample problem. So what is the conjugate base of HNO3? Note that this is acting as the acid. It's telling you the conjugate base. This is the acid. So it's going to lose a proton. So it's going to lose that hydrogen. And since it only has one hydrogen, it is completely removed from NO3. And I also lose a positive sign, basically, charge, because I lose an H plus. So I go from 0 minus 1 gives me NO3 minus. So here's the conjugate base of this acid. I've lost that proton, I've lost the hydrogen, but I've also lost a positive sign. So I go from 0 minus the 1 that I lose with the hydrogen, going to minus 1. And of course, I don't write the minus 1, but that's what it is. Okay, I will give you a chance to try your hand at B, C, and D. Let's take a look at one more problem. Label each of the species in the following equations as acid, base, conjugate base, or conjugate acid. The question is going to ask you for the acid and its conjugate base, and then the base and its conjugate acid for both A and B.